Okay. Recording in progress. Okay, dear colleagues, let us start our seminar. Today, our speaker is Alexander Povolotsky from Dubna and High School of Economics. Okay, we can start.
Okay.
Please.
Thank you very much. I would like to thank the organizers for inviting me to give this talk. I will tell about some calculation of some quantities in some models. This is project that is ongoing during last like 3 years. And the last part of it has been obtained in collaboration with Nastya Trofimova from Gran Sasso Institute in Italy. What is the motivation of this work? Is basically, we all know that integrable systems provide us with plenty of very nice mathematical structures. But for application, it's important that integrability usually suggests that exact solvability. We believe that if the model is integrable, we can extract some observables from it. But usually it's not a simple problem. Usually, even if you manage to relate the natural variables of the model to the observables, you still need to solve some spectrum, some complicated spectrum of complicated operator, solving some algebraic equations, and so on and so forth. The aim of my talk is to show you example of the system where the observables can be obtained exactly. So usually the observables, the difficulties which I mentioned, lead to the fact that you can obtain the observables in the thermodynamic limit or for infinite system. But I give you the example where in finite system you can obtain the concrete numbers. These examples are related to so-called Razumov-Stroganov combinatorial stochastic point of XXZ quantum spin chain or six-vertex model. And its special structure is due to its relation to a stochastic model. It has a special structure of the stochastic process, which at least makes, for example, the largest eigenvalue of the corresponding operator exactly known. And then it turns out that there appear some combinatorial, nice combinatorial structures, which when people discovered it, they start to obtain this result by usual combinatorial arguments. It's still, however, not simple because the relation of these models to combinatorics is sometimes either conjectural or very non-direct. And my aim here is to show how you can obtain the certain results which can potentially be obtained from combinatorics from the standard tools of the quantum integral models like beta-ansatz and TQ-Baxter equation. Basically, this is the plan of my talk. I first make a short introduction to percolation and O1 dense loop models. Then I will present the first results, which I will discuss, and sketch the steps of solutions necessary to achieve these results. And the main part is the so-called the solution proposed by Friedkin, Stroganov, and Zagir of the Baxter for the Baxter TQ equation at the combinatorial point. And then I will extend these results to the odd circumference. And also I will present the results on these models on the tilted lattices. And finally, I'll conclude. So first, let's go to percolation model. The percolation is formulated in terms of lattice, and you choose you take bonds of this lattice and say that the bond is open or black with probability p, or closed or white with probability 1 minus p. And usually the first question which you're asking, if you have a large lattice, what is the probability that there is a cluster, connected cluster of black bonds, which are shown in red here, that connects the two sides of the lattice. Okay. Basically, it is known. This model has been studied very, very actively. And it is known that it's clear that when the probability p is small, then you have many small clusters of open bonds. When it's large, then you have almost all lattice filled by the open bonds, and so you have a single huge cluster with some holes. And these two pictures on the sides here are basically statistically dual to each other. So holes here are clusters here. And there is a well-defined border between these two regimes, the critical point. It's known that on the infinite cluster, on the infinite lattice, an infinite cluster, connected cluster exists with probability 1 when p is greater than 1/2 and doesn't exist if p is less or equal than 1/2. This was proved by Keston in 1980. And then at the critical point and around the critical point, this is a typical situation of the second order phase transition. And then you are interested in the quantities which could characterize the universal behavior at the critical point. And in particular, what I'll be talking about is the statistics of finite clusters and the effects of finite geometry on these statistics. Basically, what is interesting here is this is always the critical, the models and critical points are supposed to be conformally invariant. And then it would be interesting in particular to observe how the conformal invariance shows up in this statistics. Well, the percolation itself at the arbitrary p is quite difficult to study, and there are many probabilistic methods to work with it, but it's not yet exactly solvable model, and it turns out that it's exactly solvable model at a special point, and exactly at the critical point, where it's related to another important model, which is called O1 dense loop model. So basically, ON dense loop model is formulated as follows. You consider the square lattice, and you draw the paths on the edges of the square lattice, which pass through every edge, turn 90 degrees at each vertex, and never cross. So basically, you have a picture like this. And then this number n in the name ON suggests that as far as you have a closed loop, you give it a statistical weight n. And I will be interested at the situation when the probability distribution on the loops is uniform, which means that the statistical weights of all loops is equal. It is and is equal to 1. So it's O1 model. Well, in the situation when n is equal to 1, you can actually construct this model locally. You just put at every vertex, you put this two version of vertices with two non-crossing arcs. which either go this direction or this direction. Okay, and then you put this at every vertex, each with equal statistical weight or with probability 1/2, either this or this, and then you give this O1. Okay, I will consider the O1 model on the cylinder, and I will first consider the cylinder of odd circumference. So you have the strip of width L, which is even and equal to 2L. Okay, and then you have a periodic boundary conditions. And if you draw the loops here, then first of all, when your cylinder is of infinite length, then with probability 1, all paths form a closed loops. And there are two sources of loops here. There are contractible loops, which do not go around the cylinder, and there are non-contractible loops. Non-contractible loops are shown in red here, and contractible loops are shown in blue here. In principle, I can also draw so-called defects, infinite lines, infinite paths from minus infinity to plus infinity. But this configuration will have a zero probability under the measure I just described. And I will study the two quantities, densities of loops, density of contractible loops and density of non-contractible loops. Well, why I tell about this model after I told you about percolation? Because these two models are connected. Well, to show these connections, we take the loop configurations, then construct a 45-degree rotated square lattice by putting the vertices of the sides of new lattice to every second face of the original lattice in the checkerboard order, like this. And then we connect them in this way, and you get a square lattice. And then you associate on the new lattice if the edge of the new lattice are crossed by loops. You say this is closed bond, the white one, and if it does not, you say this is open bond, and you have then the picture of the percolation clusters like this. Okay, so basically, when you put these plaquettes, this probability 1/2 as in O1 model, then you have open and closed bonds with probability 1/2, which means that you are in critical point, the percolation in critical point. Of course, there is no any critical point on cylinder of finite circumference. But if you send then the circumference to infinity, you will see just the critical behavior in the infinite plane, and which on the finite cylinder of finite circumference will be revealed in the finite size corrections to our densities in the universal finite size corrections. So let me now present first result, and first I will tell a little bit of the story how the calculation of these quantities was done before. So first attempt was undertaken by Temperley and Leap in 1971. And in this paper, exactly in this paper, they invented the famous Temperley algebra just to solve the model. And they obtained basically the infinite plane limit. So in the infinite plane, of course, there is no non-contractible loops, only contractible loops. And they have this limit. Basically, they obtained this number in the form of integral, which they didn't calculate it numerically, and they just gave a numerical value of this number. And then Finch and Adamczyk in 1997 observed that this integral can be calculated to this number. So it took more than 26 years to calculate this integral. Then the next step was to look at the finite-size corrections. And when you say about the model at the critical point, and you calculate, for example, a free energy of the model, usually you have a so-called finite-size expansion. You have the bulk term of the expansion, surface term related to the boundary, the length of the boundary, then point term related to the corners, and then so-called Casimir term or universal term, which is basically predicted by the conformal field theory that describes this critical point. So basically, you have this type of universal finite size corrections. And in 1998, Kleban and Ziv made a prediction for the universal finite size correction to this density. They predicted it to be this number. And also later, from the analysis of the beta-ansatz analysis of the related integrable models and the conformal field theory and Coulomb gas theory, people also predicted the density of the correction to the density of non-contractible loops, which vanishes in the thermodynamic limit. And finally, there are some gives all the loops, the density of all loops. So you have correction to non-contractible, contractible, and there are some. Okay, so and the first result which I want to present is this. This is the exact expression for the density of contractible loops, which is given for the cylinder, infinite cylinder of even circumference 2n, and then it's given as explicit function of the number n. And if you calculate them, these are rational numbers like this, and you can use a Stirling formula to make a finite size expansion, and it gives you indeed the value predicted by temporary lead, the thermodynamic value, and then the universal finite size corrections, and also you can produce as many non-universal finite size corrections that follow the universal one. I shown only the one of the order n to the -4. Well, and a similar result for the density of non-contractible loops. You also have a formula in terms of the gamma functions, which is calculated to some rational numbers. And then you can also obtain asymptotic expansions. And also there is a universal finite size correction, the first order, the leading order, which was predicted from the conformal field theory, and then the non-universal ones. Well, now let's look what is necessary to obtain this number. Well, first I would like to discuss what is special about the O1 DLM model and why it attracted so much interest. Basically, first, let us look, as I said, you can construct the configurations of the dense loop model by attaching the vertices with the two vertices with two arcs in it. And then we can think about it as about action of the transfer matrix to construct. So we cut a cylinder at certain horizontal layer, and then constructed layer by layer by acting to the transfer matrix. And to introduce the transfer matrix, you should first introduce a space at vectors at which this transfer matrix will act. And basically, this space will span the vectors indexed by so-called partial non-crossing pairings of L points on the outer boundary of an anomaly. Basically, what you see here, you look at the half of the cylinder from the top, and then you see which point is connected to which in the lower boundary and the lower part of the cylinder. Okay, so you may have a pairs of points connected by half loop, and also you may have infinite defects. Okay, and then I put the hole here, and I connect the point to the hole in the center. So this is the configuration where these and these points are connected by a half loop, and these 2 points are connected to defects to infinity. And here all points are, this is perfect match, all points are paired. Then the transfer matrix of the dense loop model X is a sum of pictures like this. So they basically, this is the annulus which this is the outer boundary with the points, and this is how they are paired, and this is the hole in the middle, and then you act by this picture to this picture, and you remove all the closed loops, and you obtain a new picture out of it. It's pretty clear from the picture how it acts. Okay, and then your transfer matrix will be just the sum of pictures of 2 to the L pictures in total of all possible these plaquettes. At every horizontal position you put 1 of 2 possible plaquettes. So in total you have 2 to the L pictures and like this, and you sum up and act to this picture, and this will be the action of the transfer matrix. Well, it's quite clear that if you then divide this sum by 2 to the L, you will get simply the matrix, which is a transition matrix of the Markov chain. And the transition matrix of the Markov chain has a stationary state, and corresponding largest eigenvalue of this matrix is non-degenerate, and its eigenvalue is 1. So the eigenvalue of the transfer matrix of the dense loop model will be 2 to the L. And now it's natural question to study its stationary state. So we look for the stationary state eigenvector. You can, for example, for a small system, you can explicitly construct your transfer matrix, and then to diagonalize it. And that's turned out that basically the stationary state eigenvector has a very interesting structure related to combinatorics, which was observed by Razumov and Stroganov in 2001. They found the following, that if you calculate the eigenvector, its components, its coefficients, will be such that you can normalize them in such a way that all the coefficients will be integers. And then the sum of this, and the minimal integer being 1, and the rest are some larger positive integers. And then it turned out that the sums of these positive integers are related to so-called alternating sign matrix, numbers of alternating sign matrices, and these are the coefficients themselves to their refined enumerations. And then this discovery initiated a lot of activity. People started to look at the combinatorial structure of the stationary state, calculate different averages of observables over the stationary state. And of course, since all these coefficients are integers, the correlation functions, the observables will be just given by rational numbers. And people started to take just finite systems, experiment with them, and make a lot of conjectures about relations to different quantities of these models, to different enumerations of the alternation sign matrices and other combinatorial problems. So, as I said in the beginning, my aim is to obtain these observables from the analysis of the evolution itself rather than from the stationary state, using the toolbox of the integrable systems. And what helps me in this way is the relation of the O1 model, or N model, to the six-vertex model, which is well known to be integrable. Okay? The six-vertex model is as follows. You take a square lattice, you draw an arrows on the edges, and then you have in such a way that every vertex have two incoming and two outgoing arrows. And then you have 6 types of vertices. Alternatively, you can think of this model as putting these vertices into the sides of the lattice so that the neighboring sides, the vertices in the neighboring sides would be compatible, so that the same arrows would be on the edges. Then the statistical weight of a configuration is just so we assign 6 weights, which I call A1, B1, C1, A2, B2, C2, to the 6 possible vertices, and the statistical weight of a configuration is a product of weights of all vertices in the picture. And then the partition function is just the sum of the statistical weights over all possible compatible configurations of arrows. Well, how to relate this model to the ON loop model? This mapping was made by Baxter, Helen, and Wu in 1976. This is as follows. The mapping goes through the so-called directed loop model. So you take configuration of the dense loop model, which I showed you in the beginning, and give an orientation to every loop. So you put arrows on the loops. And then you can now do 2 things. You can either sum over all the directions of loops and you turn back to the undirected model, or you can sum, remember only about the arrows on the edges, but sum up over the resolution of the vertices. And then you have exactly the vertices of the 6-vertex model. Well, if now I assign the weights A1, B1, A2, B2, I introduce 2 parameters, U and Q, and say that U to 1/2 will be this, A1 and B1, U to the minus 1/2, A2 and B2, and C1 and C2 will be this. So what these parameters are responsible for? Basically, U to the, you can see that the weight U to the 1/2 is exactly on the vertices where there is a horizontal step right, here and here. And here, horizontal step left and has U to the minus 1/2. And the parameter Q to the 1/4 is the weight of the clockwise turn, the quarter turn, 90-degree turn. So here you have two clockwise turns. So you have sorry, here you have clockwise and counterclockwise. Two clockwise turns. Yes, you have q to the 1/2, and here you have two anti-clockwise turns. This is q to the -1/2. So basically, if you assign these weights to the vertices, then every contractile loop has exactly have four say clockwise turns more than anti-clockwise, or vice versa. Then the weight of undirected loop will be q plus q minus 1. And the each non-contractible loop either makes L steps to the right before closing, or L steps to the left. So this u to the L over 2 plus u to the minus L over 2. So you have two parameters, two weights, n and v, which is assigned now to contractible and non-contractible undirected loops. And then you may calculate the partition function of the six-vertex model divided by 1 over. So suppose you have you put it on the torus with periods L and K, then divide by K and L and send K to infinity, and you have a free energy per side, free energy of the model, of the six-vertex model, or with parameters Q and U, or of the loop model with the weights N and V assigned to the contractible and not contractible loops. Okay, and then so the summary is as follows: when you are going from the six-vertex to loop model, you obtain from the parameter Q of the six-vertex model the weight of the contractible loops, and from the parameter U of the six-vertex model the weight of the non-contractible loop. At the exactly when your weights M, they should be N is mistyped, and V are equal to 1, which happens when Q is equals to U to L over 2, and both of them are cubic root of unity. So in this case, this sum, both weights will be equal to 1, and will be exactly Razumov-Stroganov point for the six-vertex model, and will be exactly the stochastic point for the simply the O1 model. And then to obtain the densities, you need just differentiate your free energy with respect to the weights. Okay. And now I'm going to actually calculate this free energy and this density, calculate these densities of weights. Well, to this end, I will introduce our matrix. I just take the new weights parameterized in this way. There are three parameters, U, Q, which are exactly the parameters I showed you before, and another parameter X, which will play a role of spectral parameter of our six-vertex model. Well, note that when I set X equal to Q minus 1, the vertex weights become just those which I shown you on the previous slide, which give you then the weights of the contractible and non-contractible loops in the O and the Q model. Well, then I want to introduce the transfer matrix of the six-vertex model. Now I'm talking about very standard procedure, and I will be very sketchy here and skip most of the details. So the transfer matrix acting on the space, which is a L product of L two-dimensional spaces. And this ways it spans the basis of vectors indexed by up and down arrows. These are vectors assigned to up and down arrows on the vertical bonds on a single horizontal row. And then the transfer matrix will be, so I construct the product of operators, Rij, where Rij acts on the extended space, our space H, times the auxiliary space. And Rij acts non-trivially in the pair of spaces as a matrix R of X, which I shown you on the previous slide, and identically in the other components. And I trace this product and get the transfer matrix, layer transfer matrix of the six-vertex model. And then to obtain the partition function, I just take a case power of transfer matrix and trace it over all remaining spaces. And to go to the infinite cylinder, I just take a log. Well, now I have to go to the limit. To calculate the free energy, like here. So, and this limit gives me that the free energy will be given by the log of the largest eigenvalue of my transfer matrix T. Any questions at this point? No. Okay. So now there is a standard Bethe-Ansatz procedure, which I also skip. I just mentioned very well-known facts that basically the six-vertex transfer matrix, it preserves the number of errors in a row, and hence I can decompose my space into spaces with fixed numbers of up and down arrows. The number n indexes this n, and the eigenvalue in this sector with m up arrows will be given by this expression, and this expression depends on the numbers m numbers xk, which are given by the solution of these Bethe equations. These are complicated algebraic equations in principle, there is no way to solve them exactly, but we go we take the way around. So what I need to do here, I need to identify the largest eigenvalue. And it's principle, people who work with the Bethe-Ansatz, they usually know that the largest eigenvalue for this regime of the six-vertex model belongs to the sector when m is the half of L. But actually, to my knowledge, it's not still proved rigorously. But in our case, where the transfer matrix is related to stochastic process, the situation is simpler. Basically, we can relate our spin basis, our arrow basis, to the loop, to the basis of arcs, which I've shown you before, in this way. So again, you give orientation to loops with the coefficients responsible to turns. And then from oriented loops, you go to the arrows, basically to the spins. Well, sorry? Okay. So basically, what I wanted to show you in this, when I discuss this basis, this link basis for the loop model, was the following. From this picture, it's obvious that this stationary state, you remember I had pictures where I had links pairing two points, and I have infinite defects linking point to infinity, to the center. But the stationary state, it's from this picture, it's basically clear that when you evolve this chain, if you have two defects, they always finally merge and only loops remain. And that means that stationary state will contain only perfect matches, well, or all points are paired, no defects. And under this linked spin correspondence, it's clear that if you have even number of sides, then this subspace of perfect matchings, perfect pairings, is exactly coincides with the subspace of the M equal to L half. Okay, so there are two isomorphic spaces of the same dimension. Well, and now how to do this? As I said, it's no way to solve these equations, but we go in a different way. If you look at this formula, if you look first of all at the formula of your transfer matrix of R matrix, you will see that the matrix elements of the R matrix are Laurent polynomials in the square root of x with powers from plus L to minus L. So basically, if you that means that the eigenvalue should be also such a polynomial, and if you multiply it by x to the L over 2, it will be just a polynomial on x. So I will introduce t of x, which will be lambda of x multiplied by x to the L over 2, and this is I guarantee that this is polynomial. And then I introduce the polynomial q, which is just the polynomial with the beta roots, with the roots of this equation. And you can see that this lambda is basically is expressed in terms of this polynomial, and this polynomial with shifted argument here. So basically, what I observe here, and the these beta equations turns out to be exactly the condition that division of the numerator by the denominator is again a polynomial in terms of this t of x. So basically, I find that this t of this q of x and t of x are related by this functional by this functional equation. And there is another one for another polynomial p of x, which is obtained by also applying the beta-Ansatz procedure, but starting from a different vacuum. We'll skip the details. So here, basically, t and q are two unknown polynomials, and phi is this function. Okay, and now our problem is to solve these equations. Basically, first thing that you observe that if you then multiply the argument of this equation by q squared and q to the fourth, you have the equations of similar structure, and you have three linear equations for these quantities: q of x q squared, q of x, q fourth. And then the observation of Friedkin, Stroganov, and Zagir was the following: that this matrix, first of all, the matrix of this system should be, this is a homogeneous system, so it should be, its rank should be less than 3. So what they observe is that the rank of this matrix, when you consider the stochastic point and the ground solution corresponding to the ground state, to the stationary state, is that the matrix has a rank 1, and it immediately gives you the answer for the polynomial t of x. And then you have just a difference equation for q of x. And then this different equation, you can, go to the function, more convenient to the function L by multiplying q of x by this thing. for which will be a similar simple difference equation. And this f is a polynomial of the degree 3n. So this equation fixes n coefficients out of 3n plus 1, and the remaining of them, the remaining coefficients are found from the condition that you have a pole here of the order 2n. So basically, you can solve these equations, and they have this solution in terms of hypergeometric functions. Well, this is already something, but still it doesn't give you an answer, because this is what you have exactly at the critical point. And you need to differentiate with respect to Q and U. Then you introduce, so basically there are two relations between Q and P. One of them is so-called quantum Wronskian relation, and another is exactly the expression of T in terms of Q and P. And using these relations, you can basically differentiate them. So if, for example, if you differentiate your T with respect to Q, there are two types of terms. One is the explicit differentiation with respect to Q, and the other is differentiation with respect to dependence of beta roots on Q, which you don't know. But if you differentiate first formula and the second formula, and go to the stochastic point, you observe that there is this term B, you obtain it here and here, and you can eliminate it between these two. And then you have this relation where A is this for the derivative of T in Q, and hence for the density of contractible loops. Well, this is basically gives you an answer in terms of the quite complicated expressions in terms of hypergeometric functions, but at the explicit numerical value of argument, and then you can simplify it, and you use the generalization of Kuhlmann theorem for hypergeometric function and properties of gamma functions, and we obtain the quantities which I've shown you before. And now, so this is basically all the way how to get the, how to arrive at the answer for the density of loops. But what I said is valid for the even circumference of the cylinder. And what circumference should be considered separately. Basically, you can employ the same procedure. What is the difference? The difference is as follows. Since on the odd circumference you cannot pair all the points, there is always at least one defect in the loop configuration. We go from minus infinity to plus infinity. And in the associated Markov chain, there are only configurations with exactly one defect. And then you have to, then you proceed with the same procedure as I described you. The only difference is that if the ground state of the largest eigenvalue eigenstate of the six-vertex model, associated six-vertex model, was non-degenerate before and corresponded to the stationary state of the loop model. Here you have odd number of spins, and the ground state is twice degenerate, and under the spin-link correspondence, these ground states are interpreted as linked states with directed defects. So you have basically undirected loops with directed defects, and you can direct it up or down, and this will be two versions. All the rest is the same, and now, so what about the relation to percolation? Basically, the situation is again different, because here I remind you that you put the lattice where you observe percolation, there was twice less size here. And so it was rotated lattice on faces with size in checkerboard order. So basically, if you put this lattice on the even on this lattice with odd number of odd widths, if you start here, for example, from the side of the new lattice, here you arrive at the side of the dual lattice. And so you cannot have anymore the periodic boundary conditions for percolation out of periodic boundary conditions for the loop model. The solution is just to duplicate this configuration, and then you have configuration of percolation clusters, but with special symmetry. When you turn the cylinder a half turn around, the configuration of percolation clusters turns into the dual configuration. So if you have here such a cluster, you will have here such a dual cluster. Well, this is a special symmetry, and then since there is a infinite defect, there is no non-contractible loops, but for contractible loops, the density is as follows, and then the asymptotic expansions again gives you the same thermodynamic value, and the finite size correction has the same absolute value as contractible loops in the odd case, but the opposite side. Sorry, the opposite side. Well, this phenomena was already observed before in the finite size corrections to the ground state energies to the associated x-exact chains with odd and even number of states. Well, sorry. And the last part, which I would like to tell about, is the loop model and percolation model on a tilted lattice. Our motivation is as follows. First, when I obtained the first result I've shown you, I wanted to compare it with results on densities of percolation clusters, which people calculated before, but it turned out that they all calculated the densities on the lattice of standard orientation for percolation, but these results give you, I've shown you, give the density of clusters on the lattice, which is 45 degrees. Well, then you need to tilt the lattice to obtain the standard orientation. But this is kind of was the first reason. But the main reason is as follows. When you rotate the lattice, basically, what you can check the conformal invariance. So I shown you the universal corrections, and if the system have a conformal invariance, when you consider the tilted lattice, this correction should stay the same up to the length of scale. And then the next corrections will be non-universal corrections. They have a memory of the lattice, but then they are expected to come from the operators in conformal field theory with the spin multiple of 4 because of the symmetry of the lattice. And it means that these corrections should consist of trigonometric functions of of the rotation angle multiplied by 4. And this is what I want to check. Basically, the system I consider is as following. You take the cylinder of the circumference.
Sasha, we have 5 minutes.
5 minutes. Okay, I
Okay.
will finish. 5 minutes. So basically, you take a cylinder, you cut it in vertical direction, and then shift and glue back. So I will have this type of periodic but twisted boundary conditions. So the vertex of a cylinder will correspond to get. So I introduced two numbers, m and n, and l, such that m plus n times l will be even number, and then I go from vertex n steps down, n steps up. So n steps down, n steps up. And then I return to the same point. So this is basically this boundary condition. I should identify these green dots here. This will be periodic boundary conditions. And to achieve this, I do the following. Let us look at the R matrix, which I introduced before. And I calculate, before I use this R matrix at a particular value of spectral parameter 1 over Q. And if I put here a difference values of spectral parameter 1 and 1 over Q squared, I get these, only these vertices, non-zero vertices here. And it looks like I took the lattice and just cut the vertex in this direction or in this direction. And then the trick which was proposed by Fujimoto in 1994 was the following. Let us construct the lattice as follows. We just construct the square lattice, but from the non-uniform transfer matrix. You put here, say, M vertices scattered in this direction, then normal vertex, L normal vertices, then M vertices constructed in these directions, and this L times. But then we alternate in different order. So basically, we introduce the non-uniform transfer matrix, where some parameters are x and some are x over q. And also multiply these transfer matrices with different parameters n times and n times. And you have this lattice, so these small segments means that you should cut it here. You cut and you stretch and you just get your lattice with tilted boundary conditions. And then you employ the same procedure of TQ relations, and it looks the same, except that your function phi has more complicated structure. And these relations, I don't know how to solve it with the how to get closed formulas that can be used for asymptotic solutions. But still, this is a linear system, and we can just solve it as a system of coefficients. And then the answer look like this. We can produce any loop densities, contractible and non-contractible. For this is for tilted lattice by 45 degrees, which correspond to standard orientation of percolation lattice. And oops, sorry. And well, this is another example. The interesting thing that these numbers, the length of these ratios grows very quickly. And also interesting that when you sum them up, this is contractible and non-contractible, you get the total densities are approximately twice shorter. Is there any combinatorics behind this? I don't know, or any numbers here. Well, and now the last thing is still, since I reduced calculation of correction to solution of an explicit linear system, I can solve it with arbitrary numerical precision, numerically. And this what I was looking at for the finite size corrections. Basically, as I said, the universal finite size corrections should be the same as before, up to the fact that the length is rescaled by because of the turn of the lattice by this factor. And indeed, this shows that I calculated the convergence to this number here, and it's very, very, very good convergence. And the next corrections, which are non-universal corrections, they can be fitted with these functions, which exactly contain the cosines of angles 4 alpha and 8 alpha here. So basically, it would be interesting to obtain these numbers analytically, but still, to this we need the closed expressions for the asymptotic corrections and for the asymptotic analysis, and we don't have it yet. So basically, this is all what I wanted to tell you about. To conclude, we obtained the closed formulas for exact densities of loops and critical percolation clusters on a cylinder of standard orientation for even on circumferences, and developed the procedure of calculating densities for tilted lattices wrapped to the cylinders of finite circumference, and proposed the numerics-based conjectures for the dependence of non-universal finite size corrections on the tilt. And the further problems which would be interesting to look at is to look at these models of loops and percolations with varying boundary conditions and on different lattices, for example. As I know, this model is exactly solvable on the triangular lattice as well. Then we looked at the first derivatives of the free energy, the averages, but the higher cumulants like variance or higher cumulants would be of interest as well. And also we're looking at the more general correlation functions, and this is the matter of future work. So this is the list of the literature with our publications related to the project. And thank you very much for your attention.
Okay, let us thank our speaker. Any comments? Any questions? Maybe by Zoom? No? Okay.
Is there any related models, group models and directed group models, whatever, related to 8-vertex model?
Well, that's a good question. I don't know, to be honest. I don't know.
Okay. One more question.
I just wonder about connection with Di Francesco and Justin works. Right. Your work is an extension or not? Because Di Francesco, we use some R matrix related with Brouwer algebra, but there is some similar construction for Biermann-Wenzel algebra. Do you use some R matrix related with some exception, some Lie algebra?
No, this is a simple Hecke or temporal leap actually R matrix, and they all Di Francesco and Justin also they described and worked out in details this relation of loop basis, spin basis, and this picture. It's basically much of this work is based on their findings, in fact. And the more complicated algebras, they appear for other groups, and there are also other models, more complicated loops models related to them. But this is probably also a matter of further works. This project was aimed to obtain the numbers from the simplest version, and maybe later we go to when I was in Saclay, I think Di Francesco told me that exactly about this more complicated models that would be interested to look at the same things there. But this is the perspective now.
Yes, and I want to ask again, you mentioned about combinatorics.
Right.
Commonly, combinatorics here appears when you study coefficient of eigenvalues of certain
Eigenvector.
function of certain polynomials. Do you have some kind of new information about, for example, alternating some sign matrices or tone and 15 classes of matrices, problem related with alternating matrices? Because some result was obtained by De Geer and other people's they really conjecture some meaning, combinatorial meaning of certain solutions to the O1
Exactly,
group.
yes. So basically, probably these results can be somehow interpreted in terms of statistics of alternating sign matrices, since it can be interpreted in terms of statistics of the six-vertex model, and they are one-to-one correspondence. But my aim was exactly the opposite, is to my aim was actually to arrive to these numbers not through the combinatorics and the correspondences, but through the Bethe-Ansatz procedure and all that. In particular, you mentioned De Geer. They conjectured, for example, similar quantities, the corresponding quantities in the continuous time model, in the continuous time relative on this model, so called Razumov-Peel model or continuous time of O1 loop models. And I didn't mention these results here. I also have results on calculation on proving of their conjectures in this continuous time framework by exactly the same method. You also have this TQ relations and so on, and this allows to obtain certain combinatorial structures like probability of certain how it's called bracket sequences, you know, or these loop structures. Well, these quantities were not conjectured before, and they are like they are new, but their continuous time relatives, they were exactly obtained as conjectures from the combinatorial consideration, and then it became possible to prove them via the Bethe-Ansatz and TQ equation, this Friedkin-Stroganov-Zagier technique.
Okay, one more question, Tole. We have no time.
We have time? No time?
No time.
No time, okay. So I just wonder about Bethe-Ansatz. You mean the TQ version of Bethe-Ansatz, or you mean a string version of Bethe-Ansatz?
No, I mean what I just told in the talk. You obtain the Bethe equations, and then yes, you derive TQ equation as a condition of, so Bethe equations are in a sense equivalent to the condition of divisibility of certain polynomials, which becomes TQ relation, and then you solve the TQ relation. What was done here is solution of the TQ relation. No strings.
Okay, thank you. Let us thank our speaker again.